Hello everybody, this is Professor Jing. This week we're about to embark on the most important theoretical topic so far. The concepts we will discuss here are abstract and many students find the materials challenging to fully understand. This topic will build a bridge from our foundations of producing data, exploratory data analysis, and statistical distribution to our final goal of the course, which is statistical inference. Our motivation question for this section is statistics we calculate from the sample varies. And so, what does their distribution look like? Here is the objectives for this lecture. So first, we want to distinguish between parameter and statistics. Be able to define sampling distribution, distinguish between population distribution, sample distribution, and distribution of sample data, and determine whether statistic is an unbiased estimator of a population parameter. Meanwhile, we will find the mean and standard deviation of sample distribution of a sample mean, calculate probability involving sample mean when population distribution is normal, and explain how the shape of the sample distribution of sample mean is related to the shape of population distribution. And lastly, we're going to apply the central limit theorem to help find probability involving sample mean. In the next chapter on inference, we will be interested in estimate unknown population proportion using the data from our sample. For example, here we may wish to estimate the true prevalence of diabetes or true prevalence of obesity. Although we can find the prevalence of diabetes in our sample, which is 7%, and the prevalence of obesity in our sample is 12%, we don't know how close they are likely to be the true values. In order to know that, we will need to learn more about how much this sample proportion might vary in repeated sampling. If we did this again, how different might the result be? We can't just guess the answer. A parameter is a number that describes some characteristic of the population. In statistical practice, the value of a parameter usually unknown because we cannot examine the entire population. A statistic, on the other hand, is a number that describes some characteristic of a sample. The value of a statistic can be computed directly from the sample data. We often use a statistic to estimate an unknown parameter. A parameter is a number that describes some aspect of the population. These are fixed quantities, which are usually unknown. Some of the examples will be the population mean, the population proportions, and the population standard deviations. But there are many more. Here we see the notations we will use to represent these concepts in our course. To represent a population proportion, we will use the lowercase letter p. To represent the population mean, we will use the lowercase Greek letter mu, and to represent a population standard deviation, we will use a lowercase Greek letter sigma. We use these notations when we discuss the theoretical concept of discrete and continuous probability distribution. In fact, we use them because in those sections we were also assuming we knew those values for the entire population. A statistic is a number that describes some aspect of the sample. Some examples will be the sample mean, the sample proportion, and sample standard deviation. But again, there's many more. For the sample mean and sample standard deviation, we use some notations as in Unit 1. X bar represents the sample mean, and the lowercase s represents the sample standard deviation. The only new notation is the p hat, which is used to represent the sample proportion, which is the number of successes over the total number of trials in the binomial experiment. So parameters are numeric quantities that summarize some aspect about the entire population. Clearly, these are usually unknown to us in most research questions, and statistics are numeric quantities that summarize the sample. If we draw a sample from the population over and over again, we will start to gain a picture of how the statistic p hat behaves. Where is it centered? How spread out is it? How can we calculate probability about it? Etc. This is the idea of a sampling variability. Let's look at sampling variabilities for quantitative variables. Now looking at the height of males in the entire US adult population. On the left, we have an extreme large sample and the theoretical distribution drawing. It is reasonable that we have good estimations for the mean and standard deviation of the height in this population. And the height are also well approximated by a normal distribution. In this population, the US adult male, we have the population parameters. The population means are the mu equal to 69 inches. The population standard deviation sigma is equal to 2.8 inches. Then on the right, we have two samples. In the first sample, we have sample mean X bar is 68.7 and the sample standard deviation is 2.95. These sample statistics are different from the exact values in the population, which is not surprising. In the second sample, the sample mean X bar is 69.1 and the sample standard deviation is 2.66. These sample statistics differ from both the population parameter and the statistic in the first sample. If we repeat this over and over again, we will start to gain a picture of how those A statistics behave. We will be most interested in the behavior of the sample mean. Before we move on, let me point out that this histogram gives a good demonstration of how we might expect the sample from a normal distribution to look. Notice that they're not perfectly normal or even perfectly symmetric. This is why we must be cautious about making strict judgment about the shape of our population based upon our sample without a careful study. Our sample will vary, and although on average the process will represent the population well, we can observe rare instances where it does not. The concept of bias and variability relies on the idea of repeated sampling. In the top left plot, we have estimates which on average hit the target, and so are unbiased. And the points are very close to the target, and though the process is producing estimate with the relatively small variability. On the top right plot, we have estimate which on average do not hit the target, and so are biased. The points are still very close together though, and thus the process still produces estimate with relatively small variability. In the bottom left plot, we have estimate which on average hit the target and so are unbiased. Here, however, the points tend to be very further from the target, and thus the process produces estimate with relatively large variability. In the bottom right plot, we have estimate which, on average, do not hit the target, and so are biased. The points tend to vary further from the target, and thus the process also produces estimate with relatively large variability. It is clear that we would like an estimator that is unbiased, means on average. It will not overestimate or underestimate the target. Another statistical way of saying this is that the expected value, or the mean of the statistic, is equal to the parameter. And we want our estimator to vary as little as possible, have the minimum possible standard deviation. If we know something about how the variable our statistical will be, it will help us make informed decisions about the location of the parameter. For example, if we know we are in the top left case, we will be more certain that our estimate is closer to the true value than the bottom left case, where the variation is much greater. They're both unbiased, but we will clearly prefer less variation. In practice, decreasing this variation usually requires increasing our sample size, and this will result in increased costs to conduct the study. So a balance is often found that does the best possible with the sources available. Sample proportion arises most often when we are interested in categorical variables. When we record quantitative variables, we're interested in other statistics such as the median, or the mean, or the standard deviation of the variable. Sample means are among the most common statistics. Consider the mean household earning for the sample of size 100. Compare the population distribution on the left with sampling distribution on the right. What do you notice about the shape, center, and the spread of each? When we choose many samples from a population, the sampling distribution of the sample mean is centered at population mean mu and is less spread out than the population distribution. When sampling is from normal distributed population, then the distribution of the sample mean will possess the following properties. First, the distribution of x bar will be normal. Second, the mean or the mu of the distribution of x bar will be equal to the mean of the population from which the sample were drawn. Third, the variance or sigma of the distribution of x bar will be equal to the variance of the population divided by the sample size. Most population distributions are not normal. What is the shape of the sampling distribution of sample mean when population distribution isn't normal? The central limit theorem states that if we repeatedly draw samples from a population and calculate the mean of a variable or a percentage, or those sample means, or the percentage will be normal distributed. It is a remarkable fact that as the sample size increases, the distribution of a sample mean changes its shape. It looks less like that of the population and more like a normal distribution. When the sample is large enough, the distribution of sample mean is very close to normal, no matter what shape of the population distribution has, as long as the population has a finite standard deviation. How large a sample size n is needed for the sampling distribution to be close to normal depends on the shape of the population distribution. More observations are required if population distribution is far from normal. No matter what we're measuring, the distribution of any measure across all possible samples, we could approximate a normal distribution as long as the number of the cases in each sample is about 30 or larger. From the population, we could take all possible samples of a given size n, and for each sample, we compute the sample proportions p hat. We will then prepare a frequency distribution of p hat by listing the different distinct value of O hat along with the frequency of occurrence. The frequency distribution will constitute 3 sampling distribution of p hat. The mean of the distribution mu is equal to the true population proportion p, and the variance of distribution sigma is equal to p times 1 minus p over n, and the standard deviation of the distribution is equal to the square root of the variance of the distribution. Here is a summary of formulas for this chapter. I'm not going to talk about these formulas as the book does a great job explaining how to use them to calculate the basic probabilities. This is all I have for this lecture. Please let me know if you have any questions.